Okay, hello everybody. We are today introducing the Datatable package, which is a Python library that is dedicated for manipulation of data. This is a primary data manipulation library that is used in the Driverless AI, where Driverless AI is, as you know, is our main product of our company. And even though Driverless AI is commercial, this library, which is the foundation of the Driverless, it's a foundation, meaning that it's at the bottom level of it. It is open source and free for everybody, and we like to speak about it from time to time. So we started a series of meetups. Approximately, we will hold them once a month. So today is the first introduction. Then the next meetup will be at the end of February, and after that at the end of March, and so on. So what is a data table? Data table is a library for manipulating two-dimensional data frames. So pretty much the same as pandas. Only when we started the project in 2017, we quickly realized that pandas is not sufficient for our needs, because even though it works beautifully with smallish data sets, as soon as you want to move to larger data, you quickly run into all sorts of problems. And the Datatable library was designed to solve those problems. So the core features that we wanted to introduce were the big data support. So we have customers with really big data, and by really big data we mean here big data for a single machine. So it's not the scale of petabytes yet, but the scale of hundreds of gigabytes is something that we can handle. So we wanted it to be as fast as possible, because for automated machine learning you need to process the data very fast, because you want to try all different combinations of generated features, and the speed is important. So we decided that it will be implemented purely in C++, as opposed to pandas, where large parts of it are implemented in Python, and then some of that is recompiled using CPython to achieve better speed, but it's still not the same as having a native C++ code. Then we also wanted to have a data set. We also wanted support for out-of-memory data sets, and these are data sets that reside on disk. We'll talk about that in a moment. We also want to have the virtual columns. These are the columns that are computed on the fly and therefore save on memory. And we want also, for better speed, we wanted all algorithms to be multi-threaded, because in modern machines we have multiple cores. On this laptop I have 16 cores. On servers we have 40 cores, and on some of them even 256 cores. This is something that is routine nowadays, but when, say, pandas started, multi-core machines were rare. So not all. So pandas was not designed with multi-threading in mind from the very beginning. And finally, the API, we'll talk about how we structure calls to Datatable. We wanted to be something which is extendable, and we drew inspiration from the R Datatable, and which in turn was built upon SQL, but it's not exactly like SQL. We'll see what it means in a bit. So today, Datatable is maintained primarily by two people, by myself and Alexei here. But we also have C contributions from external people from time to time, and of course we always welcome those, and if you would like to contribute, we would also welcome you to do so. So the platforms we currently support: Mac OS and Linux, both x86 and PowerPC platforms, and we will be adding Windows support in the next version. This is something that we're currently working on. So the next slide is what the table is not. So we do not position ourselves as a library that will replace pandas, because we do not think that everything is a competition and we need to squash the other library to be considered the best. So what we think of pandas is our friend, and similarly other packages such as NumPy, Arrow, Dask, and all the ecosystem of Python packages, that all do similar things a little bit differently, but it is important that we have all of us to support each other and to see what's possible. Because if there was no NumPy and no pandas, how would we know that we do something as best as we could? The only possibility to challenge ourselves and to achieve good results is to know what is possible, to know what others have achieved, and try to beat them. So we think we love our competition, and we want to support them, and both in code and in everything else. So the niche where Datatable can be used is first of all working with the big data, as we do in our company, but also if you really need to squeeze out performance. If you need support of NA values, we have uniform support for NA values for all column types. I think Pandas has recently, in the latest release, they added NA support for integers, but that's only happened like a month ago. So we have this support for all columns from the very beginning, and we also allow for fast data access, both from CSV files and from binary files, because many of the transformations allow are to read the data, modify it, and then write it back to disk, or process or to send it over to some other process, or anyways. There is lots of serialization going on when you deal with data, and this is something that Datatable tries to optimize as well. So let's talk a little bit more in details about the core features. So first, I have said that we have C++ code mostly, and by recent count, it's like 96% of the code is in C++. And we consider ourselves mostly debt-free in terms of code, which is to say that we spend a lot of effort on refactoring our old code and making sure that we don't have something that is out of date and or needs a replacement. So we're trying to build a library that is friendly to contributors, and a library that we would be happy to support for years to come. And which is why we also supporting contributions. And an important thing to notice is that we trying to maintain no dependency policy. That is to say, in terms of Python dependencies, we currently depend only on two small libraries, Colorama and Blast, and we are planning to getting rid of these two small dependencies in the next release. Because basically we observe that whenever you have any kind of dependency, there will be a configuration of packages where it will break. Even with these small and similarly inconsequential dependencies, and that have no binaries in them. And lastly, our binary dependencies are also kept at the minimum. So at the in the beginning of our development, we relied on several binary libraries, such as LLVM, for example, OpenMP, and so on. But over the years, we have removed all those dependencies, because every time when we found ourselves that we require some external library, binary library, it becomes really difficult to deploy it in a consistent way across multiple user configuration machines. So today we have wheels that have no built-in SO files in them. That is, they install cleanly on the user system, whether you have macOS or a Linux machine, and they do not bring any external libraries with them, which means that it's highly unlikely that it will clash with whatever existing configurations you have on your machine. So next feature, as I talk, we had in-memory and out-of-memory data sets. So what does it mean out of memory? So sometimes the data is big and too big to fit in your memory. Let's say this laptop has, I think, 32 gigabytes of memory, but what if I wanted to process a 100 gigabyte file? So obviously it wouldn't be possible with a convenient package such as a NumPy or pandas, but in this case, memory mapping comes to rescue. So what is memory mapping? Is when you have a data set on disk and then you are opening in a special opening the data set in a special mode called memory mapping, and you work with that data as if it was in your RAM, but in reality it's still on the disk. So you're not consuming your system RAM at all, or to the minimal amount, while you're still able to process the data, maybe a little bit slower, but at least it gets the job done. And in order to achieve that, the data set has the package and the data and all the formats have to be in the format that are compatible with each other. So it's not like you can take any old data set and just memory map it and use it. It has to be in a specific format. So we designed this specific format so that the data representation on disk is exactly the same as it would have been if it was kept in RAM, and this allows us to interoperate between RAM and the disk. And another scenario that is very common for driverless AI is when you have multiple processes and you need to send data from one process to another. So usually if you were doing it with regular Python, you would say that, okay, I need to serialize the data, or maybe pickle it, and then send that pickle over some kind of communication channel to the other process, and then open that pickle. So that involves a lot of copying, and which means that again it consumes memory and it consumes time. So in our case, you don't need to do any of that as long as you store your data set in either in a RAM disk or a plasma store, which is another kind of RAM disk, or maybe you can just store it on a plain file system level, and the operating system is smart enough to know that if you stored something just now, then it keeps things in cache, and in a moment it will, if you open that same file, it will not even it will not even send it to disk. It will just read it from memory. So exchanging data between processes becomes really fast. All you need to do is serialize the data set, and then you can give the handle into another process, and the other process can open it immediately and without any extra copies. So next feature that we mentioned are virtual columns. So virtual columns is our name for computed columns. These things have been known for quite some time. I mean, even in Excel, you can have a column and you can have computed values, though they are not really at column level, but rather at cell level. But still, there is a notion that you could have a column that is a mathematical function or some kind of transformation of another column, and many of the transforms that we are doing in data science are actually this kind of function of another column. So sometimes you don't need to materialize that column. That is to say, you can just save the idea that your new column is a function of the original one and just use it like that without having to store that extra data in memory. So again, this addresses a common situation where you have a large data set, you open it, and then you start creating new features, and quickly your memory, you have eaten on your memory and you're running out of memory. So in that case, having virtual columns allows you to spend your memory budget much more slowly. So, and there are many other advantages, as you can see from this list. For example, when it allows us to more easily interoperate with other libraries, because instead of saying, for example, saying that give me data from another library and I will just copy it into my format, instead of copying it to my format, I'm just on the fly convert it in the format that I understand, and without creating a copy. Or taking a subset of rows is extremely common. I don't need to actually copy the data into a subset of column. I can just mark the columns that these are the rows that I want to select, and then just use that. Joining can be a very memory-hungry operation in other packages, but in Datatable it's kind of simple. We just create a mapping between which rows, map to each rows, and all of the columns become virtual. So it's basically a very little memory is used during joining, and this approach allows you to create really big joins. For example, even cross joins that would be unthinkable of in other languages or in other packages. So grouping is done similarly, basic arithmetic operations and so on, and we are thinking of extending this approach to other venues. For example, we want to have compressed data columns. This is the last row. It is not implemented yet, but we want to have compressed data rows. If you have really big data and you really want to process it, you may try to compress it, and that would allow you to squeeze it into your memory. You can encrypt the data if you are processing sensitive data that you would rather not have lying around in the open. And of course, the sparse data set is a typical example of the data that can be accessed virtually. So multi-threadedness, another feature, as I mentioned, that we started from the very beginning. We said that we wanted everything to be multi-threaded. So currently, all the data-intensive operations are multi-threaded, and whenever we think of any operation that would require processing the entire data set, possibly millions or billions of rows, we always think about how to make it in a parallelized fashion. And with unfortunate exception is whenever we need to interrupt with Python. As you know, the Python is inherently single-threaded, and access to Python is not possible in a multi-threaded fashion, in true multi-threaded fashion. It is possible to control the degree of parallelism, that is how many threads a worker is used. So sometimes you may find that using all possible threads may be a little bit too much, and it chokes your system. So maybe you sometimes want to reduce the number of threads, especially if you are having several data tables in different processes running at the same time. If both of them were trying to use the maximum number of cores, then they will just starve each other. So you want to probably reduce the number of threads. And we are not done yet. We are still thinking constantly on how we can further improve those algorithms, how we can improve our performance. Now let's take a look at the library itself. So the main class we have is called simply frame, and it is an equivalent of pandas data frame. So this is a two-dimensional table of the data, so it's no surprise there. Then we have helper functions, which is buy, join, sort, and update. They roughly correspond to the same named SQL verbs. That is, you can do group by, you can do join, you can sort, and you can update, and we will see shortly how they actually used. Now we have this little F symbol. F symbol is used to refer to columns of the frame, and we also will see how it is used. In the main namespace DT, we have many helper functions, such as, for example, reducer functions, but obviously I did not list all of them. There are probably around 50 or so. Then there is a namespace for math functions, and there are also models. Datatable, even though it's a library for manipulating data, it has some built-in models, in particular aggregator models and FTRL model and some others. This is something that we will be talking about in subsequent meetups. So the main class is a frame class, as I have mentioned. This one is written 100% in C++, not even in 96%. So it has basic properties as one would expect. It's a number of rows, number of columns, its names and types. And in the underlying level, a frame is just a simple vector of columns. But importantly, a column is an internal class. It is not visible in Python. So whenever you selecting even a single frame, a single column from a frame, you're still getting a frame. You never get a column object. This distinguishes us, for example, from pandas, where whenever you try to select a single column, you get a series object. And sometimes we saw that it sometimes leads to confusion and incompatibilities. When you have a data frame, you want to get a series of the other way around, and some functions work on one object and not work on the other. We don't have any of that. We have just frame. And important thing to notice is that we do multiple levels of caching and not caching but sharing of the data. So for example, a frame is a vector of columns, but each column is a shared pointer, which means that whenever you select a column from a frame, you're not actually copying any data, you're just getting a new pointer to the same data. So this operation takes no time. But at the same time, we are using the copy on write semantics. Copy on write semantics means that if you were to try to modify the data, then at that point we would see that, okay, you have two pointers to the same data, which means that we now have to create a copy and modify the copy. So this allows you to efficiently extract parts of the frame and modify them as you need, without worrying about your copy affecting the other objects when you least expect it. At the same time, if you're not planning to modify it, then just selecting parts of the frame becomes really, really fast. So we're also trying to memorize the basic statistics of each column. So whenever you try to access such as minimum, maximum, the count of NAs and so on, they're stored with the column information itself, so that accessing those properties repeatedly is fast. And as we mentioned before, columns can be virtual, which means that they may be computed on the fly, but whether a column is virtual or not is completely transparent to the user. So you don't have to worry about this distinguish unless you're trying to maximize the performance and trying to think about how it's all laid out internally. So now the fun part. So the previous slide said we have main class, which is frame. We also have a main function in the library. So this is something not very traditional to have a main function, but basically we are saying that everything that we would like to do with a frame, we want to do through a single function, which is a square bracket function. And this comes directly from the data.table. So if you're familiar with data.table, you know what this slide means. But if not, let me walk you through it. So if you look at on the right-hand side, there is a SQL column, and the standard SQL query looks like this: select something from a frame, and there is a where condition, then there is a group by condition, a join condition, and an order condition, and so on. So, and most of the things in SQL are done through this command. Occasionally, you would switch the verb. Instead of select, you would say update or drop or delete. But other than that, it's a single command. So in data table, we also have a single command. Instead of 100 or so different methods that you would apply to a frame, and you would need to remember which parameters are and so on, we have just a single method that you need to memorize. So let's look what it does. So it has the following components: I and J, those are required, and then all the others are optional. So you can specify as many and as little of them as possible. So basically DT with the square brackets IJ means that select on the from the frame. I means which rows you want to select, and J means which columns. And here, which columns or which rows is a very flexible, so you can put whatever you want in there. And additional operators modify this the statement, so you can say by, in order to say that you want to apply this operation by certain groups. Join means that you want to also join something, and then with the joined frame do the same operation. And also a sort verb, which means that I also want to sort the result.
Does the joined frame have to have the same shape?
No. Join means that it's basically like a key operation. So you have a one column in the main frame, and then there is a join frame, and we join them by a column that serves as a lookup key, basically. So join is like a dictionary lookup.
Okay, joining column. You have a joining column between the two frames.
Yeah. Yes. So there is also so as I said that the main square bracket is equivalent to SQL select statement. SQL delete statement is using the Python del keyword, which is delete, the same thing. So notice that you can delete pretty much exactly the same thing as you would otherwise select it, right? So you can have arbitrary complexity queries there inside the square brackets, and it will delete that whatever that query returned. And similarly, update in SQL is just an assignment operator in Datatable. So whatever the right-hand side is, complex queries that select some elements, we can assign a replacement to them, and that will update those elements. Okay, so what about those IJs, and what can we use in them? And we adopt the approach that, well, whatever you want, as long as it can be meaningful and unambiguous. So, which is why we are saying that instead of adding new syntax, we are inventing new syntax. So, for example, you can obviously integers indices to select columns and rows at specific indices. Strings for column names, slices, range objects. You can use a frame to select a certain a subset of rows, for example. You can plug NumPy array or Panda data frame. You can plug a type. A type as a column selector will select a columns of a specific type. You can list any of the above. You can put a dictionary to rename things. And of course, you can use expressions and to make computation on the columns. So what are their expressions? So here's an example coming from Pandas. So if you wanted to add to columns, you would say frame and square bracket A as the name of the column plus frame square bracket B. If a frame is actually a longer name, for example, it can be my dataset underscore train or something, then we just unnecessarily repeating that frame name multiple times over. And if you have an expression that is more complex, it becomes cumbersome. So instead, we are doing a little bit differently, which is we use the square bracket notation. So we say frame, then in square brackets, first comes a colon. Colon means that everything. So it's slicing everything. So first position is a row selector. So we're taking colon on the first position, just take all the rows. And the second expression is a column selector, as you remember. And for the column selector, we have f.a plus f.b. And that f dot just basically allows you to refer to the column A and column B without having to repeat the name of the frame. So we think of the f as a shortcut for frame currently being computed on. And f.a is just a column named A, and it doesn't have to be even in this data set. You can use f.a in any data set, and then whether it will have a column A or not having column A, it will be selected. With the function export.names, export underscore names, you can even assign those f expressions to variables, and you can say a comma b equals frame.export names, and suddenly A and B become simple handles to the columns named A and B. you can even rename, so you can even have a simpler handles than the actual names of the columns that you actually have. So once you have simple handles, so here in the last expression, a and b are really just shortcuts for f dot a and f dot b, because sometimes this f dot is a little bit too repetitive. So selecting a sum of two columns is just frame square bracket colon a plus b. That's it. Okay, so what else can we do with this f symbol? We can overuse this f symbol. We like it a lot. So f dot a is a single column with a simple name. If you have a little bit more complicated name, that is, you cannot put in a variable, then you would use f square bracket and you put a name of that column in a variable or just as a simple string. And you can also use indices to refer to a specific column by index. You can also use slice, and it could be either numeric slice or a string slice to refer to multiple columns at once. So the f notation can refer to can select multiple columns at once. And you can and the last example, fint, shows that you can even use a type to select the columns of a specific type. So fint selects the integer columns, and that expression that selects only specific columns can then be used in whatever other places, ij, by, sort, and all other clauses. So here is an example. Whenever you have multiple column and you apply a function to it, then that function is automatically applies to every single column within the function. So in the first example, say we say min of f float. F float selects all the float columns. Then when we apply min to all the float columns, then it just expands into min of each a list of means of every particular column. So the first expression just returns the means of all float columns in the frame. The second expression, we first select f colon 3, just selects first three columns. F minus 3 colon is the last three columns. So basically, we're just saying that give me the first and the last three columns of the frame. The last expression, dt colon int equals float. So int as a j selector means that select me all the integer column, and when we assign a type, it actually means a typecast. So we selected all the integer columns and we casted them into a float type. So all the integer columns became floating point columns. And we also have row-wise function, such as row min and row any and row all kinds of row functions that can take multiple columns and apply a reducer in the row-wise fashion that is across the column. So row min of f basically means an average of all the columns in the f, and then you can apply any kind of restriction to that f. So for example, f colon minus 1 means all the columns other than the last, and maybe the last one is a target column. So you would say row min of f colon minus 1 means take me the average of value in every row, but do not take into account the target column. And the last expression is a little bit shows how you can combine all those different expressions. So f square bracket colon means select me all the rows, all the columns. Is an a function applies to it, means that for every column find out where the NAs are, and row any means that look for the within all those columns applies the any functions, which is basically the same as Python any. That is to say, are there any NA values in all the columns in every row? And if there are any NA values, then we are applying a del operator, that is, we are removing those rows. So the last expression basically removes all the rows where at least one value is NA. So this is how we see the data table. Basically, these simple verbs, we combine them together as a building bricks to construct an expression of arbitrary complexity. So as opposed to, for example, a pandas would say something like, would invent a new method for that, saying I don't know, remove all column, all rows with an ace or something like that. So we want really to have this building blocks, almost like Lego, that you would be able to think about new expressions and new ideas that you can represent. Okay, we are almost at the end. If you want to hear more about Datatable, you're welcome to visit our GitHub repository and documentation website. We are on the readthedocs.io, and we are currently in the process of improving the documentation. So maybe next time, if we in a month when we meet, it will be in a much better state. But basically, if you want to install Datatable, it's super simple. We want to keep it that simple always. So it's just pip install Datatable, even though it's a binary package. And you may be saying that you may be used to having to install it from Conda and from other more obscure sources, but we support the most Pythonic and most simple way of installing things, which is PyPy via pip. And then using Datatable is just you import it and start coding. So if you have questions, which I mean not today, but in the future, then please feel free to ask them on Stack Overflow. We recommend Stack Overflow for asking, and we are constantly monitoring that website. And just because when you ask it on Stack Overflow, it's easier for other people to see and to benefit from your knowledge, whereas on a GitHub, it's a little bit harder for Google to find the questions and the answers there. So, but some of the questions may be more appropriate to ask on GitHub. So you're free to ask there as well. And of course, we are always welcoming new contributions if you want to get involved more with the project. And the contributions are not just the code, just discussing things that you like, that you don't like, features that you miss, errors that you see, and so on, are all always welcome. And please feel free to visit our repository. So now we come to the question and answer part. So anybody have any questions? Yeah.
So what's the performance, your performance benchmark against like pandas or NumPy? What kind of thing have you done to do performance comparison?
Okay, so the question is, what is the performance gain compared to NumPy? So
by yourself, just
yeah. So this is not an easy question in the sense that for different tasks and for different workload and for it will be drastically different.
Right.
So
pick someone that
pick someone in my favor. So the one that goes most in my favor is the one where we read the data, the binary data from disk, because we do not actually read it, we memory map it. So it takes a microsecond for a data table, and may take several seconds or minutes in pandas or NumPy, so the proportion of millions. So reading CSV files, for example, is we need to read, and pandas also need to read, but because we have the multi-threaded code for that, and pandas using a single-threaded code, we can be as much as 10 times faster. For other things such as sorting or grouping, we can be on some tasks we can be several orders faster. On some tasks, pandas could be a little bit faster. It really depends, because they also started to working on improving the performance of their code. So you will see that it's really varies from question to question. But generally, we see that the memory usage is much better with Datatable. So on some of the tasks that pandas would just crash with out of memory errors, Datatable is able to handle them quite nicely and quickly. Yep.
So in the virtual columns, right? So the virtual columns.
Mm-hmm.
So even though it is memory mapped and all the stuff, but like you said, you can load any kind of data. It all depends on how much memory you have on your machine. That's a limitation.
So the limitation is really your hard drive space, and that is hardly a limitation because you can just buy a new hard drive, and they are relatively cheap. I mean, we would recommend using not the spinning, but this SSD drive, yes, for faster disk access. But basically, you're not really limited to the amount of RAM on your machine. But you might sometimes you might have to be careful to not to use some of the operations and to save the data to disk from time to time in order to if your usage starts going pretty high. But you should be able to work with the data of hundreds of gigabytes of size on a laptop. That's our goal. Other questions? Yeah.
Thank you. Presentation. I have a question about the SQL syntax.
Mm-hmm.
You said that the data table can perform some of the SQL operations, correct?
So we do not support the SQL language, so you cannot give a SQL query to Datatable and expect it to execute the query, but we support the same operations that a SQL query would otherwise perform. So we have a slightly different syntax, and it might there might be a little bit differences here and there, but mostly whatever you can do with SQL, you should be able to do the same with Datatable. Yeah.
Can you maybe talk a little bit about what you might cover in the subsequent meetings?
Yes, so our current plan is for the next meeting to have a more hands-on session where we would take a data set and just try to process it with Datatable and see how it looks like with a real sort of example. And later on we will also dedicate one session to models such as FTRL and maybe aggregator that we have. And I think that this is it. Maybe we'll have multiple sessions with dealing with concrete examples. Yep. All right. If there are no more questions, then thank you all for coming, and please come back again.
Sorry.
Yeah.
You talked about the multithreadedness in C++, but
Yeah.
only the Python portion is single-threaded, right?
So, yeah. So explain it. Yes.
I understand that part, but like, is there any bottlenecks in terms of usage? And I'm trying to load up a lot of data, but which portions are single-threaded? Limited.
Oh, yes. So basically, anything that you do with Python is inherently single-threaded, and there is almost no way of circumventing that. But if your data is not originally residing in Python, and originally residing in Python means that, for example, it's in a Python list or in a Python dictionary. So as long as you don't have that, if your data avoids going through Python, then there is no bottleneck. And avoids going Python is a standard way. So, for example, when you have a data in your CSV file, you read the CSV using Datatable, then the data doesn't go into Python. Data directly goes into the data table. Or if you read some, I don't know, arrow data set, then it goes into the arrow, and then we can load it from there, and it again avoids going into Python. So as long as you are not creating like pure Python objects, such as pure Python lists, pure Python dictionaries, and so on, you will be good. And you feel free to create those objects if the data is sufficiently small, or maybe for a reduced data set. But having 1 million rows loaded into Python and then back will be slow, unfortunately. Yeah.
So what's your vision for a data table next few years?
So our current plan involves we will be adding support for new column types. So we still want to get up to speed with the arrow project that is supporting many different column types, but they're not as advanced in terms of the manipulations that you can do with those. So we want to start supporting the date columns, the array columns, and all the different column types. We also want to see how we can optimize our performance. We also want to add more interoperability with different projects, in particular in terms of visualization. We would need to work with other libraries to create some kind of interfaces that they should be using or we should be using in order to make this interoperability possible. Because most of the current libraries for visualization, say Matplotlib, Seaborn, and so on, they developed in a pure pandas sort of world where only pandas existed, so they catered to that object, and it's easy to do anything with pandas. For any newcomer project such as ours, we are fighting an uphill battle to saying that yes, we also want to get visualized, we also want to interoperate and so on. So we'll be working on that. But otherwise, we have a roadmap on our GitHub repository. So if you visit the repository and it's search for roadmap in the issues, there are things that we want to implement for the next version. That is approximately the end of spring, and then we'll see that's as the needs arise, basically.
Is there a killer, in many pieces of software, there's some killer app, something that it does extraordinarily powerfully. Is there something that it might take a while to proceed? Is there such a thing that you found here?
I think the killer thing would be that it can actually handle really big data, and this is something that we want to continue working on, to expand that thing, because well, if we can do it and you actually have that big data and you cannot do it through other packages, then this is a killer, right, for you. So yeah.
At the very beginning, you mentioned something like when choosing C++, they give you ultimate performance, right?
Mm-hmm.
You mentioned that one. So, had you chosen another language other than C++, what would the performance would have been? So, like, by your estimation, so how much you gain by choosing C++ compared to other things?
Well, there are other languages that are compared to C++ in performance, let's say Go or D, but they are C++-like. Right. So we did not strongly weight it on relative benefits, but they're pretty much the same. The crucial differences here is between C++ versus Python, interpreted language.
Right.
So,
so are you saying that the most benefit you get from Datatable is by implementing a lot of things in C++ or others?
Yes. So by implementing through C++, we gain access to really low-level stuff, such as we manipulate our threads directly. We implement, we fine-tune fast loops, and.
But you can easily mess up as well. You can easily mess up some the low-level things as well.
Yeah.
You can do it for boosting, and you can do, if you mess up, really mess up that low level.
Yeah, that's true.
Okay, that's what I'm saying. That you have a double-edged sword.
Yeah, but also Python is written in C, right? So it's nice to communicate with Python if you write your program in C++, because then you can include some Python stuff and you can directly.
I mean, C++ has other benefits than not only speed. It's also much. It has strong typing,
Right.
so that eliminates a lot of possible bugs that would otherwise crept in Python code. It's a stronger, let's say, class object-oriented architecture there with templates and everything. But it's really a choice. I mean, I'm not saying that Python is bad. Python is is good for its own need, but whenever you have a large project, having a really large project in Python becomes complicated to manage. All right, thanks again.